Good morning. Now I'm going to talk a little bit more from the software side, and it's about multi-devices support and OpenMP extension. So the question is, what is the relationship of OpenMP with the MEEP project? So we will check this motivation. Why are we working with OpenMP? And we will show you some kind of new execution and new data directives that we have developed inside the BSc and in the MEEP project, and also how we have supported full data dependencies in this version of OpenMP, some evaluation results that we obtained, and finally the summary of this part of the talk. So what is the motivation? As Fran explained to you previously, we're going to create some kind of accelerator, and this accelerator will have two ways of being used. The first option to use this accelerator would be to use it as a self-hosted accelerator. That means that it will contain all the elements, all the infrastructure in terms of software to work as a standalone accelerator that would connect with other accelerators and coordinate the work among themselves. But there's another option, and it's to use this as an attached accelerator. We know this from the GPUs, from the NVIDIA, for the AMD GPUs, that we can use a host that has the operating system and connect it to several, or maybe one or more, or multiple accelerator devices. And this is also something that we want to support in our architecture. So, and this is what I'm going to talk about here. Usually, for doing this kind of using this kind of attached accelerators, OpenMP, the language, is used. Since OpenMP 4.0, one is able to upload parts of the computation of your program to an accelerator. For doing this, we have a directive called target. The target directive allows you to specify the ID of the accelerator you want to use and to map parts of your memory, from your host memory, to the device. We can see it here in this graphic, in this diagram, that we are not only uploading the execution of the program, but we are also mapping the data. Mapping could mean that you copy the data or that you just make a reference to it. It depends if you are in a unified shared memory environment or not. But this is not important at the moment. Inside the device, we can have other subdivisions, like for example, in the NVIDIA GPUs, the usage of blocks. So we can spread also the inner parallelism inside the devices. It's not only the target directive that we can use. We can also use some related directives, like the ones for spreading the inner parallelism in the device, target teams distribute parallel 4, or the ones that allow us to allocate or delete data in the devices without performing any uploading of execution parts. But as we saw in our project, we will have more than one accelerator. So what do we do with OpenMP if we want to use all the accelerators that we have in our host? So what we have at the moment is that we will have to manually program these accelerators, and this has the disadvantage that we will have to create these coordination programs for all the applications we want to write. Every different application will need a new implementation of the coordination. Or we could just extend the language and offer this support automatically for the programmer so that the programming of multi-devices is easier for them. So in the MEEP project, we have been working on that, and we are proposing an extension that we don't upload only to one accelerator, but we are able to do it for several of them, multiple of them. So in this case, the model changes. We are distributing the execution among several accelerators, and we're also distributing the data, as we can see it here in this diagram. How can we do this? So the most important, or the backbone of this support, is the execution directives. So what we have done is to extend the target directive, and we have created a new one that is called the target spread directive, which allow us to specify not only one device. In this case, for example, we have the close devices that allows us to put more than one. In this case, we see that we are using the devices 2, 0, 1, and 3. The order is important because it determines what part of the computation and what part of the data are going to be mapped to these devices. So as we see in the example below, the device 2 is going to get the first 64 items. The device 0 are going to get the next 64 items of this computation and the data. But if we switch the order, we're also changing the devices where the data is going to be mapped. And this could be critical because in our computations, we need that we have the data before we work with them. So any changes in this could impact the performance of your applications. We also support the spread schedule clause, which allows us to specify which strategy are we going to use to distribute the data and the computation among the available accelerators. At the moment, we only support static using a round-robin strategy. That means that the order here is important and that we're going to be mapping each chunk to the devices that we have in the list. And if we have more chunks, we repeat from the beginning. So this is the strategy that we are using. Another important feature is the use of these delimiters, which is OpenMP spread star and OpenMP spread size, which allows us to perform arithmetic with the limits of the mapped memory inside the chunks. So we will be able to work with our chunk of data relatively to this chunk of data, and makes it easy to program our applications. So what we are basically doing is adding an additional level of parallelism between the host and the devices. The rest remains untouched. So we keep supporting the parallelism inside the devices. So it's possible to spread initially the computation among the devices, then spread the computation among the blocks or teams that you have inside the devices. And inside the teams, you can spread the computation among the threads that compound these teams. So in this example, what we have is that we are distributing 64, we are giving each of our devices 64 items or elements for being processed. Inside this device, we have 4 teams or blocks, and each of them will get 16 data items and iterations. And inside, each of the teams is composed by 4 threads. These threads will get each one 4 data elements and 4 iterations to process. Okay, but it's not only the execution directives. Yesterday, in some of the talks that we were able to attend, we saw that moving data is always expensive. It's more expensive than doing the computations. So if we support only the execution directives, we will have to be mapping data from the host to the devices and back to the host every time, and this wouldn't be performant. So we have also extended the data directives of OpenMP so that the programmer can place data into the devices beforehand and calculate how long this data is going to be there. So in this case, the target data spread directive places this data into a scope. So at entrance in the scope, you put the data into the devices in a distributed manner, and at exit, you gather the information that you have distributed. Of course, there is no way, like from the program, to know how many data elements you want to distribute, because we are not associating this to any part of the code. This is a data directive that doesn't execute anything. in the device. So we have created a new class called range that allows the programmer to specify which is the range where we are going to distribute, and a new class called chunk size that specifies how big are these chunks. The strategy is the same, round robin fashion. But sometimes we don't have in our programs the possibility to have this structured blocks of code where everything flows clean. You enter the program, you exit the program, and that's it. Sometimes you need to enter data at some random point of your program. So we also have supported the enter data spread and exit data spread that allows you to put data and not care how long it's going to be there. You will have to make sure that you delete the data from the devices by using the counterpart, which would be in this case exit data spread, but it gives you the flexibility to break this structure of your program and make this, for example, put them in separated functions that is useful when we are creating our programs. Another advantage of using these enter exit data spread directives is that they run asynchronously. So that means that you can be mapping data, but at the same time you could be executing something in your accelerator. So this is something that is not possible to do with the target data spread directive. So, and finally, we also support the target update spread directive that allows you to have the latest version of the data that you have and that you already map with the previous target enter data spread directive. We have also worked on improving the performance of our directives by offering full data dependencies support. Why is this important? We have here a very simple example of how we will coordinate different directives where we enter the data to the devices, where we perform a computation, and we take the data back to the host. So in this case, for performing the computation, you will need to have all the data calculated and put onto the devices beforehand. And if we use an asynchronous mode of mapping this data, unless we use a synchronization directive, we won't be able to make sure that the data is already there. So that's why we have added the OpenMP task wait directive right after it to make sure that all the data is there. The same applies for the execution part. We execute something and we cannot copy back to the host until the data is already on the latest state. We have added another synchronization point, and finally at exit, we perform the same synchronization using task wait. So as we can see here, because of these synchronization points, we are always going to the speed or the pace of the slowest GPU or the slowest accelerator that we are using. How can we solve this? So we have worked to offer support for dependencies among the chunks that we have mapped. That means that when we have mapped something to a device, we can continue working on other chunks as long as they are not dependent on each other. We create dependencies among different parts of the program by using the clause depend. In this case, we use a dependence out that specifies that we are creating a necessity for the next execution directive. And the next directive is programmed with depend in to specify that we are waiting for some specific chunk to continue our work. The fact that we are waiting just for this little piece of chunk allows the GPU to wait just for this, and as soon as this data is available, it will continue the execution. it's not necessary to have all the data available in the host to continue, just the chunk that is important for this device. In that way, when we do this, we are no longer dependent on the execution of other GPUs or accelerators. We just need our data, and that's it. So as we can see here in the example, we are gaining a little bit of time by using dependencies. So we have evaluated this approach in the following manner. As Fran explained to you, we are at the stage that we have now a node and one FPGA accelerator. So we cannot test this in multiple FPGAs. So what we did is, okay, we're gonna work it in the future, but let's test it with what we have now. So in the BSC, we have a CT Power 9 cluster, and we only needed one node to test this, and each of these nodes has 4 NVIDIA Volta 100 GPUs, and each GPU has 16 gigabytes of global memory. The software configuration is a Red Hat Enterprise Linux server with support for CUDA devices, and we perform the extensions of OpenMP language in Clang LLVM compiler in the front end. And we chose an app called Somier. It is like a benchmark that performs calculation of forces, accelerations, velocities, and positions of 3D arrays. The arrays come in the form of 3 cubes, each one, in this case, of 1200 to the power of 3 items, and we perform the calculation 31 times. We make this on purpose to make sure that our data does not fit the accelerator's memory, because this is the real problems that we face every day in our job as scientists. We are given problems that that are always out of memory. So not even the whole problem fits in the 4 GPUs that we had. So what was the solution we proposed? We divided the data in several buffers or several parts or partitions. So for example, if we use only one GPU, we will have to split these cubes in 12 parts. So that means that we are not going to be running out of memory on the only GPU that we have. If we have 2 GPUs, we will partition the data into 6 parts, and each of these parts will be split into 2, so that we don't run out of memory. And in the case of 4 GPUs, we will do the same, 3 parts, and then each of these parts split in 4. What were the results that we obtained? So we saw that when we use 2 GPUs, we increase the performance in approximately 1.8. When we added 2 GPUs more, means 4, we are getting 2.4x speed up. And then we also test the version using the synchronization directives like task wait, and the version using only dependencies. And we notice that with 1 GPU, the improvement is very little. With 2 GPUs, we start seeing that dependencies matter. And then when we have 4 GPUs, we really see a significant increase on the performance in the execution. So we have presented to you today a language extension for OpenMP, which includes a complete set of directives, not only for execution, but also for data movements, so that you can use them for all kinds of programs. We have presented you also a prototype of this implementation. It's something that is working, that we have implemented in LLVM, and an evaluation of this prototype, including dependencies, with the Somier microbench. We can conclude that programming models should address this multi-device approach, because as we have seen it, we are having accelerators as the execution mode, And we are not only having one accelerator per host, we are having several of them, multiple of them. And we also have learned that synchronization matters. It's better to use dependencies among chunks than using costly synchronization directives that will make accelerators wait for data that is not necessary for them. Features not presented today. We also have experimented with double buffering so that we are able to map or transfer data to the devices, and also overlapping the execution to other chunks that have no relationship among them. And we have obtained also some positive results. The delimiters that we propose, like OpenMP spread start and open spread size, allows us to work with extensive codes because if we perform the simple arithmetic, for example, OpenMP spread stat -1, we are able to take additional parts of the memory to be mapped to this device. And also we support the broadcasting of data because sometimes you want to have a copy of all the data in all the devices. So you don't always want to distribute. So we also support the broadcasting of the data to all the devices. Of course, it's up to the program to use these, the whole data. What are the future efforts of our implementation is we want to further evaluate the prototype. We have more benchmarks on the way. We are actually working now with climate simulation code for our colleagues in the BSc. They tested this with one GPU, so now we want to do it automatically with the 4 that we have available in one node. We are also working with dynamic schedulers because it's a difficult problem to solve. Static scheduling is easy because we know beforehand where our data is going to be, but if we don't know that, we're going to have problems with affinity. So, and affinity matters in this case. And we are also contributing with the OpenMP subcommittee on accelerators. We are presenting our progress with the intention that these directives or this way of programming with OpenMP would be adopted in the future. We don't want to convince them that they use this exact flavor of OpenMP. We are just trying to make some kind of awareness that every time, every day, scientists need to program multiple devices. And if we make it easier for them, then it's better. Thank you.